Okay, so let's remember what we're doing. We are trying to talk about, we're trying to do something for functions that sort of analogous to what we did for Bolzano wire stress. Like, what kind of condition is the analog of compactness, right? So a compact set, you've got an infinite, infinite set of points in it. Then you're guaranteed a limit point. Or in terms of sequences, you've got an infinite sequence in there. Then you're guaranteed a convergent subsequence. Okay, so we're trying to do that. And remember, we're sort of throwing things that are like probably relevant. The idea of boundedness, right? So like, we talked about pointwise boundedness. We talked about uniform boundedness, right? So pointwise boundedness, you remember, was that at each point your sequence was bounded, right? And then uniform boundedness was that at every point all your sequences are bounded. Okay, but you had a bound that worked for all points and every function, right? Whereas at pointwise boundedness meant that at one point you had a bound that worked you have a bound for each point. Okay. Okay, and so we're going to be sort of answering two questions. One is sort of like when can we guarantee a pointwise convergent subsequence right? So you've got some sequence of functions, and we're wondering, like, under what conditions can we guarantee a pointwise convergent subsequence? And then the second thing was, under what conditions can we guarantee a uniformly convergent subsequence? Right, and this is kind of the climax here. The theorem of Ascoli-Arzola. When can you get a uniformly convergent subsequence? Okay, so so I think we have time to do it. Let's just do it. So Rudin gives us this example, and he gives this sort of a counter example. You have suppose you've got a uniformly bounded, you've got uniformly bounded continuous functions on a compact set. Is that enough to guarantee pointwise convergence? That there will be a pointwise convergent subsequence? And the answer is no. So you think maybe that's strong enough, but it's actually not. Uniformly bounded continuous function on a compact set. And the example he gives is the answer is no. This is a question. And the example he gives is just if you look at the sine functions of increasing frequencies. It says, look at sine nx from n equals 1 to infinity. These guys, and consider them on 0, 1. Okay, and he says, well, look, if there exists a uniformly, if there exists a pointwise convergent subsequence, then you would have some some subsequence like this, some f and k. Let's call these guys f sub n. Right. You'd have some f and k that converges pointwise, right? There would exist some subsequence that converges pointwise, and that would mean that if you looked at the difference, fn. If you look at, got a little bit wrong. If you looked at, say, sine nx minus sine and kx minus sine n k plus 1x, right? then that limit would be 0, right, as k goes to infinity. Right? So that's what that means, right? At each point, this thing, if we look at like the difference between successive points in the sequence, functions in the sequence, then that would go to 0, right? Okay. And that would imply that, which would in turn imply that the limit of the squares would be 0. Okay. 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 And at this point, he pulls out a theorem. So this is a theorem that you guys don't know yet, but basically the theorem says that under certain conditions, the integral of the limit equals the limit of the integrals. So we showed that if the functions converge uniformly, then you can switch integral and limit. Okay. But there's actually another theorem that you're going to get to, you will get to if you take, anybody who takes the, Math 137, you'll get to this theorem called the Lebesgue-dominated convergence theorem. Lebesgue-dominated convergence theorem, which says that even if you have pointwise convergence, then under certain conditions you can switch limit and integral. Okay. So, so what that says is that will give us that the integral of this limit. Okay, the integral of this limit equals the limit of the integrals. The limit of the integrals. That you can switch limit and integration. Okay. And roughly speaking, this is how my real analysis professor explained it to us. The theorem says that if you have a function that looks kind of like a lemon, if you have a bunch of functions and they live inside of a lemon, then you can do this switch. And so, these guys, certainly live inside of a lemon, right? Because they're all bounded functions on 0, 1, right? They're all bounded functions on 0, 1. They live between, -1, -1 and 1, and they're on 0, 1, right? And so they definitely satisfy the conditions of the Lebesgue-dominated convergence theorem. And so you can do the switch. Okay. Right, but this limit is 0, right? This is the integral of 0. So this integral is 0, and this integral, if you work it out, turns out to be non-zero. It turns out to be actually like 2 pi. So if you just do some calculus, then you can see that this would happen. Okay, and so so there can't be a pointwise convergent subsequence because that would result in this contradiction. Okay, so so this is not enough, right? Uniformly bounded continuous functions on a compact set, not enough to guarantee the existence of a pointwise convergent subsequence. We can get, however, a kind of weak result in that direction, and that is the following: if you have a bunch of functions, let me make sure I get things straight. So you've got a sequence of complex value functions on some set. And if the set is countable and the sequence is pointwise bounded, then you're guaranteed a pointwise convergent subsequence. Okay, so Okay, so let's think about this. What's the idea? You've got a bunch of functions, and let's suppose that there's a point. Suppose you've just got one point. Okay, suppose you've just got one point, and you've got a sequence of functions on it. Right, you've got a sequence of functions on that one point. How do you know that there's a pointwise convergent subsequence? Does that make sense? If you had just one point, why is it pretty clear that you're going to get a pointwise convergent subsequence? Right, so drawing this as real numbers, it doesn't really matter. We know that the values of the fn, right, so fn x1 as n goes from 1 to infinity, those are bounded, those all have some bounds, right? It's pointwise bounded, so you know that all these values, right, if we look at the supremum of these things, it's bounded by some number, right? So how do we know that there exists a convergent subsequence? Anybody have an idea? Right. This is just a compact set, right? If we look at the ball of radius m, the closed ball of radius m, that's a compact set, right? And so we've got the sequence. We've got a sequence of points sitting inside of a compact set, and so you're guaranteed a convergent subsequence. So it's just because of compactness. Okay. So these guys. The values are all bounded, and so they're in a compact set. And so you're guaranteed a pointwise convergent subsequence. Okay, so here's what we do. That's that's actually pretty much the main idea of this proof. So you say, well, look, so you can create. So let's call it right. Right. There's a pointwise convergent subsequence. Let's call it like fn1 x1 fn2 x1 fn3 x1 and so on and so forth. Okay. Right. So we just these are the indices of the subsequence. Okay. Right. Call it this. Okay. So we're gonna part of this proof is just creating the right notation. So let's notate f1k to be f and k above. Okay. Yeah.
I feel like this is a dumb question, but why are we trying to show that there's a subsequence that's a pointwise convergence? Like, does that implies that the whole function, that the whole sequence of functions is pointwise convergent?
No. In fact, the whole sequence probably isn't going to be
right.
Pointwise convergent. So what we're doing here is we're trying to find we're trying to make an analog of these, of the other, of these theorems that say, like, if you have a sequence, you've got a convergent subsequence, right? So here, we've got a sequence of functions, and we want to show that it's got a convergent subsequence.
Right, I guess I just don't see why that's helpful, knowing if the subsequence is convergent.
So, yeah, so like I said last time, these sorts of theorems are used in differential equations, actually. So like when you're doing differential equations, you're trying to show that you have some solution to your differential equation. Yeah, so yeah, it's probably like, why do you care about this? Why do you care about this? But it's in, this course is more like, let's show you the tools, and then the tools we use later in later courses. So like in this course, they call it real analysis, but that's sort of a misnomer in many ways. It's not about real real values. It's about metric spaces, right? And then it's not really, we're not really doing analysis, but we're sort of like creating the tools for analysis. So the title of the book is Principles of Mathematical Analysis. That's actually the most apt title, right? Principles, we're just like showing you the basics of analysis, but all these tools will be used in later analysis courses, like in complex analysis, in Fourier analysis, in partial differential equations, stuff like that. So this is more like, here are the things that you're going to need. Okay. So yeah, it probably doesn't seem clear at all, why you'd want to have a pointwise convergent subsequence, but it is useful to have this ability to say, like, under what conditions, if you have an infinite number of points, in a compact set, you're guaranteed a convergent subsequence. Well, we want to do something like that for functions, and the reason is is in partial differential equations. And maybe I'll try and I don't know if we have time, but I'll try and talk about that later, maybe on the last day. Okay, so to give you some sense of why we would care. But in any case, what we've got so far, let's come back to here. What we've got so far is we've got our sequence of functions, and then we've got a subsequence that converges only on the first point of our countable set. Right? So we've got this countable set, x1, x2, et cetera, and we've got a sequence that converges only on the first point. Okay. Okay. So here's the sequence. Here's the sequence. We took our sequence, and then we got our subsequence. Okay, and I'm going to notate it like this. Okay, so f1k is going to be the kth term in this sequence. The 1 indicates that this converges on x1, right? And the k indicates that the kth element of the subsequence that converges on x1. Okay, is that good? Okay, so I'm just going to sort of sketch out how to do it. The idea, I'm going to sketch out the idea. So what you do next is you consider the sequence f1k, right, at x2, right, as k goes from 1 to infinity. Okay, so you do exactly the same thing that we did with the original sequence, right? We started off with this original sequence. We look at its values on x1. We see they're bounded, so there exists a pointwise convergent subsequence, right? And then we take that subsequence and we look at that thing's values on x2. This subsequence already converges on x1, right? We look at its value on x2, right? They're bounded, right? And so again, right, there exists a convergent subsequence. subsequence that you know, would be F1, F1, K1, F1, K2, F1, K3, et cetera, right? And so we'll notate that guy, notate that as F2K, right? So the second sequence, the second subsequence, the one that converges on X2, and we'll look at the kth terms. Okay, so we'll do that. Okay, and then you keep on going. Okay, you keep on going, and you get the sequence, right? So F11, F12, F13, et cetera, F2, F21, F22, F23, et cetera, right? F31, F32, F33, et cetera, right? So remember what these numbers mean. This means it converges on X1. These are the guys that converge on X1. These guys converge on X2, but they're a subsequence of the previous guy that's converged on X1, right? So these guys, the second sequence converges on X1 and X2. Yes? Right. The third sequence will converge, is a subsequence of this one, and so it converges on X1, X2, and X3, and so on and so forth. Okay. Okay. And so what you do is you take the diagonal. Okay. So let you know, I don't know what you want to call it. Yeah. So then, so let me just observe. Right. So so notice that each row is a subsequence of the previous. 2, the nth row converges on x sub n and all previous. All previous x case. And last, the kth element in the nth row occurs in the n sub kth place in the previous row. Right, in the n minus 1th row. Right. Right, so like the kth element here is the n sub kth element from this. Right, and importantly, n sub k is bigger than k. Right, because it's the kth element. It's the kth member of the subsequence, right? And so it's got to be bigger than k. Okay. Okay. So, and then what happens is that then f and n converges as n goes from 1 to infinity. When we take the diagonal elements, this thing will converge on every x sub k. Okay. Does that this isn't, you know, I'm sort of just giving the idea here, but does the idea make sense? Right? You create, you know, for x1, you create a subsequence that converges on x1. For x2, you take a subsequence of you take this thing and you can find a subsequence of that that converges on x2, right? For x3, and then just keep on going, right? So each row is a subsequence of the previous row, and this row is going to converge on x1, x2, x3, and so on and so forth, right? Now you're never going to get if you just look at each row, you're never going to get something that converges everywhere. The nth row is only going to converge on the first n points, right? But instead, what you do is you take the diagonal. You take the diagonal, right? And then that's gonna converge on everything. Okay, so that's the idea. Yeah, sure.
How do we know that there are like n amount of subsequences that all converge on that point?
Say it one more time.
Like, I guess I'm confused how we can guarantee that all of these different subsequences exist that satisfy the criteria of converging on like x1, x2, like.
So, I mean, are you okay with the first step? That
I mean,
if
like
you take-
making a subsequence makes sense, but
Mhm.
how do we know that there's almost like infinite subsequences for that sequence?
Why? So this is an infinite sequence right here.
Right.
You start off with an infinite sequence, and then you take an infinite subsequence of it.
Okay, so just
Right.
because it's an infinite sequence, we know that there's infinite subsequences.
Yeah, right. You get an infinite subsequence at every point. You're still going to have an infinite subsequence.
Got it.
So it sounds like you're worried that you're going to run out.
Kind of, yeah.
Yeah, but no, it's infinite,
Okay.
so you're not going to run out. Yeah, that's infinity. Okay, makes sense, kind of. Okay. So yeah, so this is really the idea. But once you have the idea, then this is sort of like the point where you have the idea and you just need to write it down rigorously. Okay. So this is not a rigorous proof, but this is the idea that gives you the rigorous proof. Okay. But that's all I'm gonna that's all I'm gonna do. Okay. Okay. So that's that, right? So whenever you've got a countable sequence, whenever you've got a countable set, and you have pointwise boundedness, right? Pointwise boundedness for your sequence of functions, then you're guaranteed a pointwise convergent subsequence. Okay. That's what we were shown. Okay. Okay. So okay. So that's all we want for pointwise convergent subsequences. Now we're going to go to the real question, which was, when do we have when can we guarantee the existence of uniformly convergent subsequences? When can we guarantee the existence of uniformly convergent subsequences? Okay. So again, Rudin starts off with sort of like a sucker question. He says, well, suppose you know that these guys are uniformly bounded, and they're continuous, and they're on a compact set, and they're pointwise convergent to start off with. Right? Is that enough? Is that enough to guarantee that there exists a uniformly convergent subsequence? And the answer again is no. Right? So no, that's not enough. You think again is sort of like piling on a lot of conditions here. It's a uniformly bounded sequence. Everything is continuous. They're on a compact set, and they're pointwise convergent. They're already pointwise convergent. Is that enough to guarantee uniform convergent? Because that's maybe what you might think, right? Like pointwise convergent on a compact set, is that enough to guarantee uniform convergence? No, it's not. Even if they're uniformly bounded, it's not. Okay. And And so again, the answer is no. And he gives this example, fnx defined as x squared over x squared plus 1 minus nx squared on 0, 1. Okay, so, and observes that, look, all of the fnx are smaller than 1, right? They're bounded by 1 because the denominator is bigger than the numerator, right? You've got a positive number, and you've got the same positive number plus something else, right? So it's smaller than 1, right? 2, the fnx, as n goes to infinity, well, you're going to get 0, right? No matter where. This is, as n goes to infinity, this term is going to become huge, and that just becomes 0. So it's converges to 0 on 0, 1, right? Right. So they're pointwise convergent. They're on a compact set. They're continuous, and they're uniformly bounded. But you don't have a uniformly convergent subsequence. You don't have a uniformly convergent subsequence because, like, here's what they're going to converge to. Right. They're going to converge to the 0 function, right? But you notice that if you take f sub n at 1 over n, what you get is 1 over n squared over 1 over n squared plus 0, right? At 1 over n, this guy becomes -1, so that this term just vanishes, and you get a 1. Okay, so that's 1. Okay, so right, so right, so the nth guy, every function jumps up to 1. Right? Every function jumps up to 1 at some point, right? And so if we want these guys to converge uniformly to 0, that means that we should be able to get them to live inside the epsilon tube, right? But if we take an epsilon tube that's small, a radius smaller than 1, well, we can never get them. We can't get anybody. we fail to get anybody to live inside the epsilon tube, right? So even though these guys converge pointwise to 0, right? Each one of them at some point is going to jump outside of the tube. So none of these guys live inside the tube. It very, very much fails to be uniformly convergent. Okay. So so even this slew of conditions isn't enough to guarantee uniform convergence. Okay. So the question is, what is enough? What do we need? What's the necessary condition? And the answer is, part of the necessary condition is a concept called equicontinuity. Equicontinuity. Okay. And equicontinuity, the way you want to think of it is basically uniform, uniform continuity. So what we need is not continuity, but equicontinuity. So where, of course, it's not uniform continuity, but it's uniform continuity. So you take your old idea of continuity, and then we make it even more uniform. Okay. So here's the definition. You've got a bunch of functions. Make this match up with my notes. Okay. So you've got f, a collection of functions, right, that go from E to some complex, to the complex point. Okay, this is my cursive F. It's been a long time since I've written it. So you've got this collection of functions, and you say if for any epsilon greater than 0, there exists a delta such that if the distance between x and y is smaller than delta, then the distance between f of x and f of y, maybe I should, since this is in the complex numbers, I'll just write it like this. The distance between f of x and f of y is smaller than epsilon for every function in your family and every pair of points x, y, and E. Okay. Then we call the family equicontinuous. Okay, we say that the family is an equicontinuous family. Okay, so just think about this, right? This looks a lot like uniform continuity, right? Uniform continuity says, given every epsilon, there's a delta, so that whenever the points are within delta of each other, the outputs are within epsilon of each other. Okay, but the thing here is that uniform continuity. So if I just say this, that would be uniform continuity for f, right? If I mark out this, right? But putting this thing in means that this delta works for every function. That delta doesn't depend on the function, right? Uniform continuity means that for you've got a function and it's got a delta that works for every epsilon, right? But here the delta is uniform across the whole family, right? Uniform continuity means across the whole set that delta works, right? This is more. Not only across the whole set, but also across the entire family that delta works. Okay, so that delta is going to work for everything, right? All the points and every single function simultaneously. Okay, that's what's uniform about this uniform continuity. That the same delta will work for all functions. Does that make sense? Is it clear what's different between those two concepts, right? Right. Uniform continuity just means that, like, if I've got a family of functions, right? Suppose each is uniformly continuous. That would mean that given an epsilon, there exists a delta, but that delta depends on the function, right? Depends on n, right? Such that if the distance between x and y is smaller than delta n, then the distance between fnx and fny is smaller than epsilon, right? There's a delta n that works for function number n, but those deltas are different. Okay. So equicontinuity, for this to be equicontinuous, this delta doesn't depend on the n, right? Okay. So remark: observe that any finite family of uniformly continuous functions is equicontinuous, right? Because that would just mean that there's finitely many guys here, right? So you'd have y. You'd have f1, f2 to fk, say. If they're all uniformly continuous, that means that each one has a delta, right? Given an epsilon, each one has a delta, right? But then you would just choose the smallest delta, right? Choose the smallest delta, that would work for everybody. So that delta, shows that, because you can do that, the family, you can find a delta that doesn't depend on the function. It works for the entire family, right? Just choose delta to be the minimum of the delta n from n to 1 to 3. Yeah. Okay. So any finite family is of uniformly continuous functions. It's going to be equicontinuous. Okay. We're going to give a condition that implies a condition that implies continuity. Okay, so here's the theorem. Let's see. Yeah. Okay. So you have a bunch of continuous functions on a metric space on some set K. Okay. If K is compact and here's the fun part, the f sub n converge uniformly, if these guys converge uniformly, then you're guaranteed that the guys are equicontinuous. Okay, we've got 5 minutes. I think we can do it. Okay, so so continuous functions on a compact set, you know that each one of them is going to be uniformly continuous, right? We saw that before. Continuous on a compact set means that uniform continuity. So we know that each of these guys is uniformly continuous. That's good because we want them to be equicontinuous. Okay. We have this other condition that they converge uniformly, right? Right. They converge uniformly. Well, that means that we can get them all within a tube, right? We can get them all within, after a certain point, we can get them all within a tube. Okay, so here's the idea. The idea is as follows. Basically, you notice that, well, they're going to converge to this continuous function, right? And that continuous function is uniformly continuous, right? Because it's on a compact set, right? And so, the guys, in the limit, those guys are going to, basically be this function, which is already uniformly continuous. And then for the guys who aren't nearby, well, there's only finitely many of them, right? There's only finitely many of them. So those finite guys are equicontinuous by what we just said, right? Those guys, we can find a delta that works for those guys, and then the guys that are really close to this, well, they'll be close enough that we can find a delta that works for them too. Okay, and then we take the minimum of the 2 delta. Okay, so that's the idea, right? We can, this convergence makes us close enough to something that's uniformly continuous that its delta is going to work for the guys who are close. The guys who are far, there's only finitely many of them anyway. Okay, so that's the idea. Yeah, nobody will be able to get it from this picture. Right? Like, this is the least illustrative picture ever. No, it's not the least illustrative picture ever. The least illustrative picture ever was what my thesis advisor said to me when I brought him something. he said, I see how it is. It moves like this. Don't you see it? And he was one of these guys who could see in 4 dimensions, right? He was a low-dimensional topologist, one of the greatest low-dimensional topologists. Of course, he could see in 4 dimensions. So he's like, yes, don't you see it? And no, nobody can see it. Okay. Okay. Okay, I've got 2 minutes. There's no way we're gonna do it. Okay. Okay. Okay, here's the idea. Maybe we can do it, I don't know. Okay, so we want to show equicontinuity, right? We want to show that there exists this delta, right? There exists a delta that works for everybody. Okay, okay. So right, that given epsilon, there exists a delta that works for everybody. Okay. So you say, well, look, these guys converge uniformly, right? So Fn converge uniformly. So so we know that there exists an n past which right, Fn Fnx minus Fmx is smaller than epsilon, right, for all x in our set. Okay. Now, I'm gonna say it like this. We're just gonna take the distance to that guy. Okay, right? Because this is gonna be true for n and m greater than or equal to n. I'm gonna take m equal to n. Okay. So there's an n. We know that past this point, all these guys are within epsilon. All those guys live within the epsilon tube of this transition point here, right? So there's this transition point where everybody gets close. Okay. So everybody past that point lives in this guy's epsilon tube, right? Okay. So actually, let me make it epsilon over 3 because I'll need that. So you say, well, look, F1 through Fn are equicontinuous, right? So there's this delta one that works for those guys. Okay. So we just have to find a delta 2 that works for the other guys, right? So this is the first observation. The second observation, you say, well, look, we know that f sub n itself is uniformly continuous, right? Fn is, just a continuous function on a compact set, so it's uniformly continuous, right? So there exists a delta 1 for this guy, such that if the distance between fnx, if the distance between x and y is smaller than delta 1, then the distance between fnx and fny is smaller than epsilon over 3. Okay, so now if you're past that, right, if n is bigger than n, well, then the distance between fnx and fny we can control by throwing in the f capital N's. So we say, well, that's smaller than fnx minus f capital Nx plus f, capital Nx minus f capital Ny plus f capital Ny minus f little ny. Okay. Triangle inequality. right? So again, I've just thrown in some zeros, right? Right. I've thrown in a 0, I've thrown in another 0, because I know I want to get close to f sub n. I want to take advantage of this property of f sub capital N. Right. Okay, but we know that this distance is small. This first distance is smaller than epsilon over 3, right? Oh, actually, let me call this. No, that is the end. Yeah, yeah. So this first guy is smaller than epsilon over 3. This last guy is smaller than epsilon over 3, right? And this guy, as long as these guys are within delta 1 of each other, right? As long as these guys are within delta 2, as long as these guys are within delta 2 of each other, then this thing is small, right? This thing is smaller than epsilon over 3, right? Because f sub capital N was uniformly continuous, right? And so all we need is that, so this works as long as, we need this to be smaller than the minimum of delta 1 and delta 2. Right? And then this will all hold. Okay? And that's it. Okay. Sorry, I went a couple minutes over. Okay, so next time we'll get to, so this was a condition giving you equicontinuity. Next time we'll see how equicontinuity gives us the thing that we want, the existence of a uniformly convergent subsequence. Okay, that's the theorem of Ascoli-Arzelà. And then we're going to do the theorem of Stone-Weierstrass. Okay, so read those two theorems over the weekend because they're kind of dense, and see if you can understand them. Particularly Stone-Weierstrass is dense. Okay, see you. Thank you. Bye-bye.
Bye.
Bye. Bye.